Before that, let's discuss what happens in cooperative coevolution, also called as the coevolution. So I break up a problem into multiple species and I maintain a different population pool for all the species. So this becomes my species 1, that's my species 2, that's my species 3, all the way up to species n. And I've got representatives of all of them, some representatives, so let's say as of now 1. Now, by cooperative coevolution, I make sure these individuals are good which cooperate with each other from all the individuals of the other species. These individuals are good which cooperate with all the individuals of the other species. These individuals are good which cooperate with the individuals of the other species. These individuals are good which cooperate with other individuals over here, and these individuals are also good which cooperate with all the other individuals over here, so they are good. However, I need one solution. Towards the end, you need to just say that which is the best solution, which is the best project, which is the best robot, which is the best navigation function, which is the best team. So towards the end, there's only one solution. You make a population, but the best individual is the one that will be used as a phenotype to solve the real problem. Finally, there's one optimized solution. Now, there's no guarantee that the best representative make the best solution. There's no guarantee of that. So now the problem is that I may have the best solution, which is made by this individual over here, not a part of the representative, this individual over here, this individual over here, this individual over here, and this individual over here. So these individual or the concatenation of this may actually make in the best solution. So let's say this was x2 species 1, x5 species 2, x2 species 3, x4 species 4, and x1 species 5. So this is the individual number and this is the species number. So maybe my best solution is in fact given by x21 concatenated to x32 concatenated to x23 concatenated to x44 concatenated to x15. Maybe that's the best solution. And this is a combinatorial optimization problem, so you need to select best individuals over here. So cooperative coevolution will give you a good mix of solution, but then you might want to solve it as a combinatorial optimization problem to get the best combination of good individuals. So let's solve that problem as well, and I don't need to speak anything about it because it is already a normal common combinatorial optimization problem. So let me give it a diagrammatic representation. So this is called as the combinatorial optimization problem, where there were 1, 2, 3, 4, 5 species, 1, 2, 3, 4, 5 species. So my problem had 5 species. So that's individual 1, that's individual 2, all the way up to individual n. And it's combinatorial optimization, so this represents species 1, species 2, species 3, species 4, and species 5. And overall, it is a combinatorial optimization problem. Which says how do I give the best combination of individuals? So that's a combinatorial optimization problem. Now, along with that, of course, I have my entire population of species 1, species 2, species 3, species 4, species 5. So that's some population over here, that's some population over here, that is some population over here, this is some population over here, and this is some population over here. Now, what this individual really is, so this points out to one population over here. That means the first individual over here is the best, the third individual over here is the best, the fourth individual over here is the best, first, and maybe the last one is the best. So I cannot throw all the pointers over here, but any individual is pointers to these population pools. So how this combinatorial optimization problem works is that I select out of these individuals, this is my population pool of the coevolution. I point out to species over here. I combine all these into one individual. I calculate the fitness function. So there's an ecosystem fitness evaluation FX. I have all the genes with me from different species and I assign the fitness function value. Then I do ranking, expectation value, selection, crossover, mutation. So that's a normal combinatorial optimization problem. So that's not to be done. Now, normally you would expect that I first solve this problem and then I solve this problem. Normally you will expect that I solve this problem and I solve that problem, and therefore the names can be given as nothing unusual about the name. So this is called as the slave problem, which is your coevolution, and this is called as the master problem, which is combinatorial optimization. And we've seen how this works, previous example, and how this one works informally, intuitively, quickly. Now, this one has the same problem as said previously. If I only use one representative, that one representative may actually be bad. If I use all of them as a representative, one fitness function value takes O(n) time. So n fitness function takes in n squared time. That's too much. If I use some representative, 2 or 3, there's a high chance that all of them become nearly the same very quickly. They become nearly the same representative very quickly. And therefore, there is a representative problem over here in all these. How do I get the representative? And now I say that, can there be a cooperation between the master algorithm and the slave algorithm such that the master algorithm solves the problems of the slaves, which is generation of the representatives, and the slaves solve the problem of the master, which is to provide good solution to the species in order for the master, who's acting like God and trying different individuals of different species to make an overall good solution. So can there be such a cooperation? And the actual answer is yes. So now let's look at, if there be a cooperation, both of them will have to evolve parallelly. So if you have a multiprocessor, one processor for this, one core for this, one core for this, one core for this, one core for this, and one core for this, they're all evolving in parallel. So let's do that. So let's start over with the slaves and then let's go with the master. So I say that I need to calculate the fitness function value of this individual, and let us again call it as the ith individual from species 1. I won't do it for all the other species, that's a repetition. So that's the one that I actually need to calculate. I need to calculate the fitness function value of xi1. So the first thing is I do it by substitution. I do a normal substitution. So I take rank 1, rank 2, and rank 3 individuals. 3 And how do I get that? I say which is rank 1 over here, which is rank 2 over here, which is rank 3 over here. So say this is rank 1 over here, this is rank 2 over here, and this is rank 3 over here. So let's do it for 1, and it'll be replicated exactly the same thing as 2 and 3. So that's the rank 1 individual over here. So intuitively, this is species 1 part. So previously I called it as, this is species 2. Previously I called it as the rank 1 of species 1. So this is species 2. This is species 3. This is species 4. And this is species 5. And this is the same individual, so it's exactly the same individual over here. So what do I do is, I take the same individual, but I rub the species 1 part of it. So what is remaining is this individual. So I rub the species 1 part of it. So I take the rank 1 individual and I rub the species 1 part of it and replace it with this individual. And I calculate the fitness function value of this. Similarly for the others too, and I'll take in an average. So that's my fitness by substitution. So I take in the top 3 ranks as per master population. So rank 1 as per master population, rank 2 as per master population, rank 3 as per the master population. I take the top 3 ranks as per the master population, and once I take the top 3 ranks as per the master population, all that I do is the same substitution. So in rank 1 I replace the species 1 part of it by this individual, and I note down what the fitness function is, and I can take in what is the average of this value around over here. So I take in the average of the same value around over here, and that is the one that I will finally use. So that'll give me some fitness function value, that'll give me some fitness function value, and that'll give me some fitness function value. I take the average, and this is the fitness function that is given for this individual. So by substitution, an individual is ranked better, an individual is ranked good if it cooperates well with the best known representatives, with the best known solutions of the other representatives. Now my problem is actually solved, because how do I know this is good rank 1, how do I know that's good rank 2, and how do I know it's good rank 3? Because it's from a master population on the overall fitness function. It's on the overall fitness function, and not previously where an individually just cooperated with a certain other individuals and got good fitness function value, and hence it was a good representative. Now there's another fitness function that you can use. So this is called as the fitness calculation by substitution. So this is defined as the average fitness value when individual I for species J is substituted in the top K representatives as per the master population. Now there's another fitness that you can actually use. There's actually another fitness value that you can use. So let's complete a few population over here. So in the previous one, from the master I was tracing slave. Now from slave, let's chase the master. So this individual is a part of this species, this ecosystem and this ecosystem. So you calculate average fitness of top K ecosystem population or master population of which XI species J is a part of. So this figure was a little bit clumsy, so let's draw a neater one. I'll only draw species 1, so that's my species 1. And in species 1, I'll probably only highlight the individual I, and I'll draw the master as well. So that's the master population. So I say this individual is a part of this, this and this. And let's say out of these 4, the rank of this is 1, the rank of this is 4, the rank of this thing is 3, and the rank of this thing is 2. So I take the top 2. So I take in the top 2. So I take the rank 1 which is here, and I take the rank 2 which is here. I calculate the average fitness of both of them. So that's my rank 1, that's my rank 2. This will be some fitness function value, this will be some fitness function value. I calculate the average of them. K is equal to 2 in our example, and whatever fitness comes out to be, it's a part of. So here an individual is given good fitness function value when it's a part of a few networks and those networks become good, when it's a part of a few solutions and those solutions become good. And the average of that is what you take as the fitness function value. So practically, if I need to do it, if I need to calculate the fitness of you people as a student, when all that you have done is participate in lots of team activities and lot of team events, so there's no way I can evaluate an individual which is you. I can only evaluate the teams that you were a part of based on their goodness. So there are 2 measures that I use. The first measure I use is I call you up on my office one day, which is this one, and I say, okay, gentlemen, tell me the top 5 teams that you were a part of and what were the performance. That's exactly what you do in your CV. So in your CV, you write down, these are my top 5 major group projects, and all these are awarded A pluses. So because you were part of 5 different teams and all those 5 different teams performed well, you may have been a part of more than 5, but you only write down top 5 projects. So you say that, okay, I'm good. But then the next thing that I can do is, which is this fitness function value, which is by substitution. So I again call you up in my office and I say that in my entire career, these are the top 5 teams that I have seen. Team number 1, 2, 3, 4, 5. So in order to find out how good you are, I put you into those 5 teams, replacing an individual, replacing somebody who has an expertise like you, and then I'll see what goodness do you provide that. So there are 2 ways you can calculate the fitness function value. You're a part of the teams in which you are a part of, the ecosystem where you're a part of are doing great, and secondly, in ecosystems which are great, you put yourself as a species and they still do great. So coming back to the architecture around, which is over here. So I randomly take in the in random population and random pointers over here. Then I fitness evaluate these up. I rank these up. I select the top K ranks, and those are used to calculate the fitness value by substitution over here. And then of course I also trace that this individual is a part of what team, and on average what are they doing. So that's how I'll get the fitness values of all these. I'll apply crossover mutation everything, I'll apply crossover mutation everything, and so on and so forth. And once I apply crossover mutation everything, so forth, I get in better population pools. Here also, after these ranks, I apply crossover mutation. So crossover is scattered crossover mutation is, instead of pointing to here, I point to someone else just to see if that's better. And I do a normal combinatorial optimization problem. And this one is specifically called as the master-slave architecture for coevolution. Where the slave tries to evolve the best population of the species but uses the master for getting the representatives and the fitness evaluation, and the master selects the best combination of different individuals from different species which together solve the problem up. And together with this, the optimization, it really happens as a cooperative coevolution manner.